Hello everyone, welcome back. So we were discussing different pre-training strategies, and last lecture we discussed pre-training and encoder-only model. Specifically we discussed the BART model, right? So in today's class we will focus on two other pre-training strategies. One is encoder-decoder only models, right? Models like T5, BART. So BART is another model, right? This is not BERT, this is BART, BART. And at the same time, we'll also discuss decoder-only models, right? Which include ChatGPT, all GPT series models, LLaMA models, and decoder-only models are essentially very popular. So encoder-only model, as I discussed, this was discussed in the last class. We saw that a new pre-training strategy called mask language model. This was used in BERT, where you essentially mask some of the tokens in the input and you ask the model to predict those masked tokens, right? This is a self-supervised approach. You don't need any label data for training, right? And being an encoder model, it essentially, the BERT model can essentially look at all the tokens present in the input. It is not an autoregressive model, right? So the entire input is exposed to the model, and you basically do a self-attention. Through self-attention, you look at all the tokens, right, present in the input, and based on that you predict the mask tokens, right? On the other hand, encoder-decoder model that we discussed here, that we discussed in today's class, we have this encoder component, right, and the decoder component, and we will see how you can best use both the encoder part and the decoder part, right, during pre-training. And then we will also discuss decoder only model. Now in the decoder only model, as the name suggests, the decoder part, if you remember in the transformer class we discussed, it's an autoregressive model, autoregressive component, in the sense like when you predict a word at the tth location, you only have access to tokens till t minus 1th location, right? You don't have access to tokens after tth location, right? So we will see how this autoregressive style of pre-training essentially helps the decoder only model learn things, right? And this set of models, right, are very popular these days. People realized over the times that encoder only model is not a right solution for a generative task, right? Because a generative task requires autoregressive setup, right? Whereas in an encoder-decoder model, right, as you require both the encoder part and the decoder part, it requires a lot of memory, it requires a lot of parameters, right? You can do all these generative tasks through encoder-decoder model together, right? But decoder model makes more sense both in terms of parameters as well as the setup, right? Autoregressive model setup itself is suitable for next token generation, right? And parameter, of course, parameter wise, you need half of the parameters than the encoder-decoder model, right? Okay, so we'll focus on this and we'll discuss this. Mask language model, as I mentioned, BERT model. It's a bidirectional model, meaning that you have access to tokens in the right direction as well as in the left direction, right? But what is required for an encoder-decoder model to essentially predict a sequence, right? Encoder-decoder architecture, you should remember, this is a vanilla transformer model, right? You have again a quick recap: input, positional encoding, right? You have positional encoding, then you add positional encoding and the input, right, input embedding, and then in the encoder part you have multiple blocks, in number of blocks, let's say 6 blocks or 12 blocks. Every block has a multi-head attention and a feed forward layer, right? This is the FFN feed forward layer, right? And this is unmasked, right, multi-head attention. And in between feed forward and multi-head attention, you have a add norm layer and the residual connection, right? In the decoder part, you again have multiple decoder blocks. Each block consists of a mask multi-head attention, right? Mask in the sense like as I mentioned earlier, when you process the Tth token, the tokens which are after Tth token are all masked, right? And then usually, the usual feed forward network. In between feed forward and mask multi-head attention, you have a cross attention layer. So this is cross multi-head attention, and through this cross attention, you essentially the decoder component, the decoder block, attends to the outputs of the encoder block, right? So this is the usual setup, right? And then you repeat this block in number of times. So now we see that in this kind of encoder decoder setup, how do we pre-train this model? Okay, so the objective is still, remember, the objective is still language modeling, right? Next word prediction can be an objective. The objective can also be, let's say, sentence classification, for example, right? So let's see. So this is my encoder block. Okay, these are the inputs. There are T number of inputs, and these inputs are called prefix, right? Now this prefix can be an instruction. Let's say the instruction can be summarize this sentence, right? Or the instruction can be find the sentiment of the sentence, right? So it can be an instruction followed by the input. Let's say in case of summarization, the instruction is summarize the following document, colon, and this is the document that you want to summarize, right? The entire thing will be fed to the encoder model, right? And after the encoder block, you will get hidden representation h1, h2 dot 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 ht. In the decoder block, when you pre-train your model, right? Let's say for a task specific pre-training, right? You also have the summary. Okay, so you give the summary here. So y1, y2, y3 dot 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 yt plus m. This indicates the summary, and your objective is next word prediction, right? So at this stage you predict what is going to come at the second stage. At this stage you predict what's going to come in the third stage, and so on and so forth. So in your decoder block, the input is y1, y2, y3 dot dot dot. This is my input, and my input is the hidden state that you obtained from the encoder block, right? And when you get at the end of the decoder block, you get the representation of the hidden state representation here, right? You pass it through a softmax, right? So this is my hidden state representation of the decoder block. You pass it through a softmax, and the softmax is going to give you the probability distribution over the token, and that's going to be your output. So this is pretty much same as the vanilla transformer model. The vanilla transformer model was proposed for machine translation, where the input was let's say an English sentence, and the output was a Hindi sentence, or output was a Spanish sentence, right? And this was the usual way of pre-training the transformer model. So now we will see what additional component we can change in the pre-training architecture, and we will specifically discuss two models. One is the T5 model, other is the BART model, BART model, right? Now, whatever we discussed so far here in this slide, I said that there is a task. The task is, let's say, summarization, right? Or let's say the task is machine translation, right? So for these tasks, you need a lot of human data, human level data, isn't it? But now the question is, we have seen in case of BERT model, we did not require a label data. It was a self-supervised approach. You basically had a running text, and you masked some of the tokens in the running text, and you wanted the model to predict those masked tokens, right? So the question is, in the encoder-decoder model, how can we use unlabeled data? Because labeled data is very difficult to collect, right? And then how do we force the model to attend to all the inputs, right? Because your output is Y, your input is X, right? Your input is fed. Your input is going to be fed to the encoder model, and your decoder model should be able to attend to all your encoder inputs, right? So let's see. So in case of BART, B-A-R-T, the full form is bidirectional and autoregressive transformer. As the name suggests, it essentially leverages the bidirectional part which was there in BART, and the autoregressive part which is going to be there in GPT, we'll discuss today, right? So it leverages both the schools, okay? So, and remember, we should be able to use unlabeled data, okay? So what is the idea here? Given an input sentence, you corrupt that input, you inject noise to that input, and you ask the model to essentially predict the right sentence, the correct sentence, right? So the question is, how do you corrupt it? There are multiple corruption approaches that they suggested. These are called noisy instances. For example, let's say your input is A, B, C, D, E, right? What you do, you mask some of the tokens similar to BERT, right? And you ask the model to predict those masked sentences, right? So in your encoder, your input is the masked tokens, the masked set of tokens, and your decoder, the output is going to be the actual set of tokens, right? So this is one strategy. The second strategy can be you can permute, right? So your sequence is A, B, C, D, E. You shuffle the tokens. It can be D, E, A, B, C, for example, right? And you ask the model to predict the actual sequence. The third one can be rotation, right? So A, B, C, D, E. So C, D, E, A, B. This is one rotation. You can again rotate, right? You keep on rotating to obtain different inputs, and your output will be the original one, right? And these are very similar because these strategies consider the entire sequence and then sometimes mask it, sometimes rotate it, sometimes permute it, right? But the length of the input remains the same, okay? They also tried out with token deletion, where you delete some of the tokens. You see here, you delete B, D, F, right? And you ask the model to predict those tokens, okay? But remember here, since this is an autoregressive model, right? You ask the model to basically predict all the tokens, not the masked tokens or not the tokens that you have deleted, right? So in your encoder, your input is going to be ACE for this strategy, and your decoder, the output is going to be A, B, C, D, E. It is not that your output will be B and D only, okay? Now this is called token deletion. They also tried an extreme approach where they essentially mask not a single token but a sequence of tokens, a consecutive sequence of tokens. For example, as you see here, A, B, C, D, E, F. A, B, C, D, E was the original sequence. You mask B, C together, right? So sometimes you mask two tokens, sometimes you mask one token, and so on and so forth. And what they said is that there is a distribution. From the distribution, they basically sampled the size of this masking, right? Sometimes if the size is 1, you just sample 1 token, you just mask 1 token. If the size is 3, you mask 3 consecutive tokens, and so on and so forth. So they randomly chose some of the positions, right? And they sample a number from the distribution, and that sample is going to tell you that what's going to be the size of the tokens that you are masking, right? So nothing fancy. This is just a way of doing pre-training, as opposed to the a sort of supervised pre-training which was used in transformer model, where you basically needed the label data. So here you don't need any label data as such. Okay, so this is my encoder. Okay, this is my input. Let's say that here you can use permute, mask, right? This should be mask, right, or delete, right? And you ask the model to predict the entire sequence. Okay, so this is BERT. Let's look at the difference between BERT and BART. So in case of the BERT model, which is an encoder-only bidirectional model, you ask your model to predict the mask tokens, right? In case of BERT, you ask your model to predict all the tokens, right? It uses encoder, it uses encoder-decoder, so double parameters, right? And so on and so forth. So that's it. Okay, so they pre-train the encoder-decoder model in this way, injecting noise and asking the decoder model to basically predict the clean version. They fine-tune the model on downstream tasks, right? So once you pre-train, you can now think of a pre-trained model which knows the language in general. Then you fine-tune. They fine-tuned it. By the way, you can also use pre-trained model for your downstream task without fine-tuning it, right? And we'll see the GPT paper, right? GPT-3 paper, which came in 2020. They showed that you don't need to basically fine-tune your model for downstream tasks. Nevertheless, on the summarization data set, they fine-tune the model on a news article, news corpus, and it turned out to be really effective. It also showed that you don't need a lot of data set, you need only a few summaries for fine-tuning, as compared to a normal sequence-to-sequence models, let's say LSTM or a normal sequence, LSTM GRU kind of models, which require a lot of data for fine-tuning. Here, since your model is already pre-trained, you don't need to fine-tune that much. So here is an output of the BART model. This is the document that was given for summarization, and this is the summary that was obtained from the model. Okay, so around the same time when the BART model was proposed, right, Google, they also came up with a method called T5. Same time, within a gap of 1 week or 2 weeks, right? And T5 is also an encoder-decoder model. It is called text-to-text transformer, right? And this is actually a very, very I would say ambitious model, right? What they said is that we map all the NLP tasks, right? Any task that you can think of, not necessarily NLP, right? Any task that you can think of, you map, or you can realize any task as a text-to-text transfer problem. It is very difficult to digest, right? But bear with me. We will essentially discuss the techniques. There is no fancy technique behind this. The same encoder-decoder model, the same corruption technique that was proposed in BERT. But remember, BERT was proposed by Facebook, and T5 was proposed by Google around the same time, right? It's kind of similar approach. But they said that first of all, you don't need any fine tuning as such, right? You pre-train on millions of tasks, right? And these tasks are all supervised tasks. So T5 data set is not a T5 training approach is not an unsupervised approach as such. Okay, but the crux of the method is that every problem can be mapped to a text-to-text problem, right? For example, let's say you want to translate an English sentence to a German. So what you do in your encoder, you write this prompt that translate English to German, right? This is your prefix, right? And then this is the sentence, and your output will be this one, the German version of it, right? So your input will be this sentence, right, in the encoder, and your output will be this sentence in the decoder. But you see here, there is a task instruction, task prefix, which was not there in case of BART, right? BART's pre-training method was very different. Now, this is the second task. COLA sentence. What is COLA? COLA is a COLA is a task, corpus of linguistics acceptability. So it basically checks whether a sentence, an input sentence, is linguistically acceptable or not. For example, the course is jumping well. Is it an acceptable sentence? No. So your input is the task instruction and the sentence, and your output is acceptable or not acceptable, right? Your input is, so the next task is checking whether two sentences are similar or not, right? STSB task. Sentence 1 is the rhino grazed on the grass. Sentence 2, a rhino is grazing in the field. Now whether they are similar or not, and you give a score, right? It is not yes or no, it is a score. Now think about it. Your output here, 3.8, is essentially a string. So you are forcing your model to produce 3.8, right? You are not predicting a number, you are basically predicting a string. And Colin Ruffell, the first author of this paper, so he said in one of his talks that, you know, believe on this this framework, it actually works. Okay, so the fourth task can be summarization. You write summarize and the entire sentence, right? The state authorities dispatched emergency crews Tuesday to survey the damage after an onslaught of several weather in Mississippi, and ... There are other tokens as well, and your model should be able to summarize this. So you can still digest these three tasks, but it is difficult to digest how a text-to-text model can produce a number. Nevertheless, they said that if you give instructions, if you write instructions, and then the task is itself, and you force the model to produce the output in your pre-training time, your model should be able to do that. So you do this pre-training. Now for your downstream task, if you have data, you want to fine-tune it, right? And your model should be able to produce. So normal encoder-decoder architecture, right? Encoder blocks, decoder blocks, right? Nothing fancy here. No change in the framework. The vanilla transformer model was used here. So for the pre-training, right? So when you pre-train, this is your, I mean, there are different tasks, and in your pre-training, what you do, this is very similar to the BERT kind of pre-training, where you basically give a sentence as an input, and then you mask some of the sentences, right, with different length. So you replace different length spans, right, with some unique placeholder. The placeholder can be the mask tokens, right? And these tokens are called sentinel tokens. These tokens are part of your vocabulary, remember this, right? So in case of BERT, you only use the single token called mask as a sentinel token, but here you are using different tokens for different masking, right? When you mask, let's say for invitation, you have a token. When you mask last, you have another token. So and the number of times you mask an input, you will have that many of sentinel tokens, right? So you are basically increasing the vocabulary, but that's fine, okay? And as opposed to BERT, where we were to produce the entire input in the decoder output, right, and not the mask inputs, but here the mask tokens. Here your task is to only produce the mask spans, right? If your input is this, thank you X, me to your party Y week, you will produce these kind of outputs. X for invitation, Y, last, and then Z can be your end of sentence sentinel, or some other sentinel tokens, right? So you are only producing the token or the span which was masked in your input. You are not producing something like this, thank you X for inviting me to your Y last, right, week. You don't need to predict the entire sequence. Okay, that's the difference. Okay, so for training they collected a lot of corpus, a lot of documents from the web, right? They use this common crawl web scraper, right? There's a non-profit organization. They periodically scrape the internet, right? And as you may imagine, internet data has a lot of garbage, a lot of noise. So they basically did a series of pre-processing to remove noise from the input. Pre-processings include removing lines which did not end with the terminal punctuation. They only retained the English text, right? They removed all non-English text, right? They also removed those tokens which look like placeholders. They removed the codes, right? HTML codes, JavaScript codes from the documents. When you scrape a website, right, there are many HTML tags, JavaScript tags, right, which they essentially removed, and they removed many duplicate texts, right? They call the clean corpus C4 corpus, and this is publicly available, right? A colossal cleaned version of common crawl web crawl corpus, right? There are 4 C's. So C4 corpus was collected for training, right? So this is their pre-training setup. They use a BERT size encoder-decoder transformer, right? It can be 6-layer encoder, 6-layer decoder, right? They basically wanted to compare with BERT. Remember when BERT was proposed, right? BERT was proposed 1 year before T5, one year before T5, and at that time everyone essentially was behind BERT, right? They were trying to outperform BERT. So in order to make a comparable model, they took a BERT size encoder-decoder model, right? And they added different denoising objectives, right? Spanning different, so masking different spans. You can also think of rotation, whatever permutation, and so on. They use C4 data, and they pre-train on this, and then they fine-tune on a series of tasks, right? They fine-tune it on the glue task. Okay, now glue is a benchmark. Glue is a very standard NLP benchmark which contains many tasks, right? For example, one task is called COLA. As I mentioned, COLA is corpus of linguistic acceptability, where given an input, your output will be whether this is acceptable or not. The second task is SST2. This is a sentiment analysis task, movie sentiment, positive, negative, neutral. MRPC, this is a paraphrased, basically whether B is a paraphrasing of A or not. STSB, there are 2 sentences A and B, whether they are similar or not, and you produce a number, right? QQP, this is again whether 2 questions are similar or not. MLNI, MM, this is essentially an entailment, whether A entails B or A contradicts B, or so on. QNLI, This is a typical question answering benchmark. RTE, whether again A entailment, whether A entails B or not, and WNLI, which is a sentence B replaces sentence A's ambiguous pronoun with one of the nouns. Is this the correct noun or not? These are all typical NLP tasks that were there when the blue benchmark was was released. And glue is actually very standard benchmark even till date, right? So they tried with glue, right? They also took CNN DailyMail corpus. This is a corpus for summarization, right? Mostly abstractive summarization, right? They took the squad data. This is a question answering data released by Stanford. They also use superglue. So glue and superglue are the standard benchmark. There are many other benchmarks these days, like Big Bench is another benchmark. Now superglue is even tougher than the glue, right? So superglue has this many tasks, and these tasks are really tough, right? Even for human being. For example, recognizing textual entailment, multi-sentence reading comprehension, Boolean question answering, reading comprehension test, and a lot of other difficult questions, difficult tasks, right? So they took glue, CNN DailyMail, Squad, superglue, and 3 different machine translation datasets, right? WNT 14, 15. So this is English to Dutch, English to German machine translation. This is English to French machine translation. This is English to Romanian machine translation. And these datasets were also very popular at the time. This is also popular these days. This machine translation workshop. This workshop is conducted every year, and they keep on releasing these kind of datasets. Okay. After fine tuning, they reported the accuracy at every checkpoint, right? So let's say a checkpoint after this many steps, after this many steps, after this many steps, these are different checkpoints. At that checkpoint, what is the accuracy? This is basically model selection, but this is not a very good approach, but it is useful sometimes to understand, whether over the iterations, whether the model is getting improved or not, right? Let's look at a series of results, okay? And here I will only show you some of the important results, but if you look at the paper, T5 paper, I think this is 50 pages paper, very long paper. There are a series of results, right, reported in the paper, very extensive empirical observations, right? A lot of abolition studies and stuff like that. But you can easily imagine the amount of resources that Google has, and only companies like Google can do this kind of research, having their GPU access, TPU access, because it really requires a lot of compute, Nevertheless, so the baseline average is their model. If you fine tune on glue and test on glue, right, this is the accuracy. This is CNN DailyMail, Squad, right, superglue. By the way, in glue there are multiple tasks, right? I think that they took only one task for this. Superglue also they took one task, or I don't exactly remember. Maybe they took one task for reporting the number, or I think they took an average, then reported the average. I don't exactly remember. And then this machine translation datasets. Baseline results, whenever you see the bold numbers, these bold numbers indicate that the accuracy is within the standard deviation. They also reported the standard deviation here, right? If something is bold, it means the number, since they did it multiple times, right? So the reported number the reported number falls within the standard deviation, mean plus minus standard deviation range. And they tested their model with no pre-training, right? You just do fine tuning on a specific task. You don't need to do this mask pre-training phrase. You don't need to do the mask pre-training, right? What you do, you take a glue benchmark, let's say, you train on that task and test it on the task, right? A pure supervised machine learning method, right? And this is the number they reported. What are the major observations? The first observation is that, as I mentioned, BERT was the best baseline that time, right? And they showed that the glue and the squad datasets, their results are quite comparable with BERT. Okay. They also showed that if you don't do pre-training, your numbers are pretty lower than your pre-training followed by fine-tuning, right? So pre-training is actually needed. Now, without pre-training, if you do training and then predict, right? For all the tasks, your model outperforms the baseline significantly, right? You see this, except for this English to French task, machine translation task, and you see here the numbers are quite close, and they argued by saying that the English to French machine translation dataset was the largest one among other machine translation dataset. It was large enough that you don't really need any pre-training as such. If you do normal training on the dataset, that will give you enough signal about this task because of the size of the dataset. If you don't have that much of data, you need pre-training. The C4 data, the size is 745 GB. The filtered data, right? I mentioned, right, a series of filtration techniques were applied. If you don't filter it, if you just you take the crawled C4 data, which is 6 terabyte of size, you see that with clean data versus unclean data, right, the accuracy is not at all comparable, right? Sometimes comparable, sometimes not comparable, right? As you see here, accuracy improves by 2%, 3% if you clean this, right? So cleaning is important, compact data is important, and pre-training on the in-domain data is always helpful, right? So they checked with 3 different architectures, right? They compared their methods with the standard encoder-decoder model that they also use, autoregressive model, right, next word prediction model, language modeling task. You see the attention head here. Now this guy is attending to all the previous guys. Look at this one. This guy is attending to, right, only the previous tokens. So this is typical autoregressive setup, GPT kind of setup. And this is a new model. It's called prefix language model, right? In prefix language model, what you do, your input is this, right? One part of your attention is unmasked, other part of your attention is masked, right? Your attention matrix may look like this, right? Now this is unmasked and this is masked. Now this part is masked. Okay, so this will act as BERT and this will act as GPT. But the difference here is that there is no encoder-decoder. There is only one stack, right? There is only one layer stack. It's not like this. In one stack, one part is acting as an encoder model and the other part is acting as an encoder-decoder model. Okay, this is called prefix LM. Now this is the figure that I mentioned. Okay, in case of encoder-only model, the entire token sequence is visible to you. In case of causal model, autoregressive model, right, you have access to one part, you don't have access to other part. In case of causal prefix model, the prefix model that I mentioned, one part is completely exposed, other part is basically autoregressive. Okay, so now let's look at the experiments, right? With encoder-decoder model, denoising objective, 2 p number of parameters, p for encoder, p for decoder, right? Now this cost is number of flops, floating point operations per second. This is the result, right? Now let's compare. So, okay, so if you think of another model where it is also encoder-decoder, but all the parameters are shared, right? The self attention is also shared, the feed forward is also shared, everything is shared, right? But you have two stacks, so you need half of the parameters, p number of parameters, right? You see, let's first understand the experimental setup, okay? Then we'll analyze the result. The third one is encoder-decoder, 6 layers, This is again denoising objective, but here there are 6 layers in encoder, 6 layers in decoder. I think in this setup there were 12 layers. The fourth one is language modeling, autoregressive setup, right? Decoder only. And the fifth one is prefix LM, right? You have all these tasks, right? For the super glue, you only these numbers are reported for the classification task only. Okay. Okay. So what are the objectives? What are the takeaways? The first takeaway is that 6 layers versus 12 layers, right? This is 12 layer. This is 6 layer. Okay. The performance drops. Right. So if you make the number of parameters half, it hurts your performance. If you compare shared encoder decoder and prefix LM, right, performance on encoder decoder with shared parameter is almost on par with prefix, right? You see numbers are quite close, sometimes worse, sometimes better, right, but on par. But of course, encoder decoder model, their model is always better, right? Always better than other models. Okay. Okay. So for pre-training, as I mentioned, they did many experiments, right? Now for pre-training strategy, they use different types of strategies. One is a BERT style denoising, where you denoise, where you basically add some of the you replace tokens by masks, right? For example, your input is thank you, mask, me to your party, and your output would be thank you for inviting me to your party. Now here interesting point is that you sometimes also corrupt, you replace a token by another token. For example, Apple week, and your task is to predict this as last week, right? Prefix language modeling objective, if you do, right, for example, your input is thank you for inviting, your output will be me for your party last week. You basically predict the next set of sequences. Reshuffling, as I mentioned in case of BART, right, your input is, let's say your output should be thank you for inviting me to your party last week. Your input can be party me for your two last fun and blah blah blah, right? Replace spans. This is span corruption. You just corrupt an entire span. The span is for inviting, for example, and you replace it by a sentinel token. You drop some of the tokens. This is again another objective that was used in BERT. You drop some of the tokens and you ask the models to predict those tokens. Okay. All right. So if you look at the experiment, right, prefix language model, this is right, and then so this is kind of this one, okay, where this is exposed to you and this is something that you want to predict. Reshuffling, BERT style mask language modeling, replace corrupted span, and then drop corrupted token, right? And you see here that most cases, if you look at glue, the dropping an entire token helps, right? Here also this is better, this is better, right? In case of super glue, I think a replace corrupted span actually works better, right? And these numbers are quite comparable, as this is better, right? So most cases, as you can see, right, sometimes this is better. So there is no clear-cut answer which strategy is better, but they did many experiments, as I mentioned, and they concluded that replace the corrupted span, right, this one, and drop the corrupted token, right, these are more appealing than other tokens. Now the other strategies, the reason is that the other reason is that when you drop tokens, your length will decrease, right? You need to produce less number of tokens, isn't it? So therefore this will also help you speeding up the training process. Okay, so now we discuss decoder only models. Decoder only models, as you can imagine, right? The strategy is not very new here, right? You don't need any input corruption as such, right? You are given a sequence of tokens and you predict what's going to be the next token. Very simple, right? Generative model that calculates the probability of the language, right? And this is the autoregressive language modeling objective that I mentioned, I think 1,000 times in this course. This is the input. You predict the next token. You essentially produce a distribution, right, over the tokens, and that's going to be your output. Then you sample a token from the distribution. You can think of it as a classification problem, because now given mod v, where v is the size of the vocabulary, you have mod v number of tokens in your vocabulary. Essentially your task would be to classify. You basically choose one of the labels. You can think of tokens as labels. You choose one of the labels from the mod v number of labels. Okay, so this is your input, right? It's a decoder only block, right? You produce the hidden state. Your hidden state will be fed to a linear layer, right, which will produce a distribution, softmax. Of course, linear layer followed by softmax. It will produce a distribution. From the distribution you sample. Okay, so nothing fancy here. Quick comparison: in case of BERT, which was an encoder only model, your input was x1 x2 dot 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 xi minus 1 xi plus 1, and this was something that you masked, right? And you ask the model to predict that masked token. In case of GPT or decoder only model, right, your input is x1 x2 dot 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 xi minus 1, and you have to predict xi. Okay, so the architecture is simple, right? And GPT-1, the first GPT paper was published in 2018, right? They use normal transformer decoder, 12 layers, right? 117 million parameters, right? Remember 2018, we are talking about parameters in terms of millions, right? 768 dimension hidden state. The dimension of each hidden state is 768. 3072 dimensional feed forward hidden state, hidden layers. Byte pair encoding was used. We discussed byte pair encoding before with this many of merges, and they used this book corpus which had around 7,000 unique books. This is GPT-1. GPT-2 was proposed just the next year, 2019. What's the difference? The difference is they use layer normalization in between different subblocks, right? Layer normalization we discussed earlier. Their vocabulary is now extended to 50,000. Context size is now increased from 512 to 1024, right? Now your data is a new data, which is a common crawl data, the same data that was used in T5, 8 minial documents, right? And of course minus Wikipedia. So this is GPT-2, and they showed that if you do unsupervised multitask learning, it basically helps. So in GPT-2, they focused more on the generation task, right? And as opposed to GPT-1, and they showed that GPT-2 starts producing more human-like sentences, right? If you write these as your input and you ask the model to essentially keep on generating tokens to fill out the remaining part, so this is your input, and these are going to be your tokens that you will essentially generate. Cost wise, quick comparison. I'm not very sure about this. I took this thing from this link, right? BERT base cost was 500 USD, I think, with single pre-training run, right? The large required $7,000, whereas GPT-2 it basically needed approximately $24,000. Then came GPT-3 in 2020, right? And if you look at the training petaflop per day, whatever, right? Significantly high. GPT-3, small, medium, large, XL, many versions. GPT-3 2.7 billion, right? And this is T5 statistics, this is BART statistics. So GPT-3, the major difference is the parameter. So we were talking about GPT-2 with only 1.5 billion parameter. Now this is 175 billion, 100 times larger than GPT-2, right? 96 layers, 96 heads in self attention component, 12,000 dimensional vectors, right? And this is the rough estimate of the cost that was taken. So three major GPT models, GPT 1, 2, 3. Parameter, as you see, increased drastically, number of layers increased drastically, data set also increased drastically, the size increased drastically. In GPT-1, they started focusing on, they said that this is the first large scale decoder only model. GPT-2, they came up with this idea called zero shot learning, right, with larger training. And GPT-3, they observed this in context learning, right? You write examples, we'll talk about in context learning later, right? You don't need to fine tune the model. You write examples, the model will be able to understand the task. And they said this is the emerging property, right? At that time they were not very sure why this is happening, right? It's very difficult to understand, dissect. Then came GPT-4 in 2023, I guess, 2023, yeah. This is a mystery because this is a black box model, right? After GPT-3, they stopped releasing the architecture, right? OpenAI was no longer open that time, right? And the exact size is not very clear, but if you look at the cost, the per token cost, this increased quite significantly, both in terms of inputs and outputs. 15 to 30 times costlier than GPT-3. This itself gives an indication that how big is the model, right? Or what's the amount of training, amount of cost that was incurred to train this model. So now GPT-4 is not only about pre-training, right? There are many additional things, right? For example, instruction fine-tuning. We'll discuss later. Instruction fine-tuning. So through instruction fine-tuning, you teach your model how to follow instructions, and then they use something called RLHF, reinforcement learning from human feedback. This is again something that we'll discuss later. Okay, so today's GPT, nobody knows what's there, right? But we can only assume that pre-training followed by series of fine-tuning, instruction fine-tuning, right? The different types of alignments and so on and so forth. LLaMA, the same thing. The LLaMA is open source. You can still look at models parameters. There is LLaMA 1, 2, LLaMA 3 is still available, right? Different parameters, dimensions, increasing dimension, number of heads, increasing number of heads, right? And they use byte pair encoding. This is also something that we discussed earlier. Okay, and they use rotary position encoding. This is also discussed. And the data set that they used is Common Crawl, GitHub data, Wikipedia data, books data, and so on. Okay. All right. So this is about GPT decoder only model. What is coming next? So in the next week, we'll talk about instruction fine tuning. Right after pre-training, this is the step that we do. Right. We are discussing how you can also design your own language model, right? You do pre-training, then you do instruction fine-tuning, and then you align your model with human feedback through RLHF, and then your model should be ready to understand the instruction. Okay, all right. With this, I stop, and next week we'll discuss the last part. Thank you.